They're actually really important. So the number system and the hierarchies and the sets of numbers, I think the best way to think about them is about the way that we classify animals. Okay, and this is something you know, you might not know you know, but you know this. So picture a cat, and if you wanted to, you could call the cat an animal, or you could be a little more specific and you could call it a mammal. Okay, right? Meaning it's warm blooded. You might call it a carnivore, meaning that it eats meat. Okay, and then if you were the most specific you could possibly be about it, you'd say, oh, look at that. That's a cat. Okay, that's a feline. Okay, so if you're not being specific, you call the cat an animal. If you're being kind of specific, you call it a carnivore. Okay, if it's a carnivore, you already know it has to be an animal, right? So that's how these sets of numbers work. If I told you that I was looking at an integer, okay, that would be more specific, okay? Because I could also call it, what could I call it? A rational number, right? Because if I'm looking at negative 19, I can make it rational by just putting it over 1, okay? So negative 19, I tell you, oh yeah, that's an integer, okay? And then if I want to be more specific, I say it's a rational number. Okay, but I'll get into that. So first, just keep this idea of the specificity, being more specific, relating to the cat. The cat is an animal. It's a vertebrate. It's a carnivore. Okay, so what are the number sets that negative 5 belongs to? That's my first question here. What are the number sets that negative 5 belongs to? So negative 5, if I take a look in here, I can see that it's not going to be able to be in this natural number set because those are all positive numbers and it doesn't include 0. Okay. It's not going to be a whole number either, even though we think of it as being whole. It's not cut up. Okay, but whole numbers have to be positive. Okay, those start at 0 and they keep going to infinity. Is it an integer? Sure it is. Okay, it's over here like the negative 19 and the negative 2. Okay, is it a rational number? Yeah, because just like in my last example with 19, I can put it over 1. Okay, so see how it says what are the number sets that I can put it in? There's actually one more that I forgot about. It's also a real number. Okay, because see how this square where all the rational numbers is fits inside that big yellow square that are the real numbers? That's how I know it's also a real number. That's why we say it's a subset. It's inside of it. So I would say integer. That's the most specific. Is that the most? That's the least specific. That's not the most. I need to decide on this. I'll decide by the end of the video. It's an integer. It's also a rational number. I think integer is more specific than rational. It's also a real number. That's the least specific. Okay. And yeah, they're imaginary numbers. You'll learn about them in high school. Okay, so it's part of all those number sets. Integer is the most specific. Rational just means, hey, I could write it as a fraction, put it over 1. Integer means, hey, that is a positive or negative whole number. Okay, so that's that one. Let's look at some more here. Are all integers part of the whole numbers set? Give examples and non-examples. All right. So are all the integers also whole numbers? Let's take a look. So the integers, you can see there, negative 19, negative 2, 0, 1, 17, and so on. There are way more than that. There are infinite numbers of them. So are the integers part of the whole number set? No. It's the other way around. See how the whole numbers fit inside the integer box? So this is no. Okay. So what we would say is the integers, contain the whole numbers. Okay. All whole numbers. Okay, it's inside the integer bubble there. So examples and non-examples. So I want an example of an integer and whole number. Okay, those are going to be the positive ones. Okay, like 0, 1, 17. Okay, just to use some from that chart, even though there are others. I could put 100 on here. I could put 3 million. Okay, so those are the examples where, yes, they are an integer and a whole number. Okay, and then the non-examples are the ones that are integer, but they are not whole numbers. Okay, whole numbers only go from 0 to infinity. That's these guys. So the non-examples would be like the -19 or the -2 or -12, -1, -1000, whatever you want there. Okay, these are integers, but they are not whole numbers. Okay, so the answer to the question is no. Are all integers part of the whole number set? No, they aren't. The examples here are 0, 1, 17, 100. Those are both integer and whole number. Non-examples are over here. The negatives, okay. Those, yes, are integers, but no, they're not whole numbers. Okay. Because a whole number has to be a positive. And it starts at 0. Why can't I move this? There we go. Okay, name 2 sets of numbers to which 3.28 belongs. Okay, 3.28, huh? Well, I knew I could go up here in the rational numbers. Okay, by the way, rational number, okay, we say it can be written as a fraction. But remember, the decimals can all be written as fractions as long as they terminate. Meaning they end, okay? Like the Terminator, he ends you. Do you guys know about the Terminator? Okay, 0.28 is 28 hundredths. And that's 28 over 100. Like that. Okay, so what else could it be? Well, it's not going to be an integer, right? Because it's got a fraction. It can't be an integer. Is it going to be a whole number? No, it's got the fraction. Can't be a natural number either. Can't be irrational, right? Because it terminates. The irrationals go on forever with no pattern. So the only one left is up here. Real numbers, okay? So 3.28 is rational. It's got a terminating decimal, and it's also a real number. It really is. It really is. Sorry. All right. Can an irrational number also be an integer? No. Can a number be a rational number but not a natural number? Yeah, if it's negative, right? Or if it's 0. Okay. Describe the relationship between integers and rational numbers. Must all rational numbers be fractions? Okay, so when you're describing, you want to, give some reasons. And this other one where we gave non-examples and examples, that's a pretty good thing to do when you're describing things. So describe the relationship between integers and rational numbers. I'm going to say all integers are rational numbers. Okay, they're a subset, meaning they're inside the rational number box, okay? Only some rational numbers are integers. Remember that rational number is a very big category. It contains all of our familiar types of numbers. We've got the integers in there, we've got the whole numbers in there, we've got the natural numbers in there. Okay, so a rational number that's also an integer, let me give an example, like negative 4 over 2. 4 halves is 2, so that's negative 2. Negative 2 is an integer. Okay, must all rational numbers be fractions? No. Okay, terminating and repeating decimals are rational. But they're not fractions, okay? All right, let's see what else we have here. All right, let's go down to this one. Oh, I did that one. Here we go. Okay, this one's from your practice. Which of the following is an irrational number? Okay, so first of all, let's remember what irrational means. Irrational means it's not terminating or repeating. Okay, square root of 25. If you don't know what that is, grab your calculator. If you don't have a calculator, just type 2 plus 2, enter in a Google search. Okay, square root button is there, 25. Hey, it's 5. What a nice number. Square root of 25 is 5. Okay, I had a student once who called square roots unsquaring. Okay, so it undoes squaring a number. 5 to the second power, or 5 squared, is 25. Okay, so if you square root 25, you're undoing it. You're unsquaring it. So that guy's he's terminating, right? It's just 5.0. Okay, he terminates, he ends. Pi, we know, is that wacky number that is the ratio of the circumference to the diameter of a circle, and it does not terminate, it does not repeat, it goes to infinity. This is all I know of pi. Some people memorize it for fun. I'm not one of those people. Okay, let's talk about 0 over 27. Okay, what does that equal? Well, let's ask the calculator. For a fraction, you can take the numerator and divide by the denominator, and that'll give you the decimal. So look what happens. 0 divided by 27. You have nothing. You share it with 27 people. Guess what? You still have nothing. They each get nothing. Okay, so and 0 terminates. Okay, so we're looking for the one that does not terminate and does not repeat. That is pi. Pi has won the irrational number contest there. The next one is a freebie, you guys. They gave you a problem that they aren't going to teach you how to do until either the next unit or the one after. Okay, so the real number system quick check. Such a bummer that it was a quick check problem that actually counts as a grade. Okay, so it says here a cube has an edge length A that is a rational number of centimeters. Identify which measurement will require the use of irrational numbers. Okay, is it the surface area of the cube? No, surface area cube is 6 times the area of one side. Okay, each side is a square with side length A. The area of that square would be A times A, or A to the second power. That's going to be a rational number. Okay, the diagonal of one of the cube's faces. So let me draw the diagonal here in another color. So if the side lengths of the square are all A, okay, the diagonal can be found by using the Pythagorean theorem. We'll call this C. The diagonal will be C. Oh, I should have made it D for diagonal. Oh well, too late. Okay, and you know, in the next unit we'll learn that you solve this by taking square roots. Remember a minute ago I said that squaring and square rooting were opposites, so I'm going to unsquare the diagonal there. So you know, here's what the length of the diagonal would be. It'd be whatever the square root of a squared plus a squared is. That's going to be irrational. Okay. Um, so that's the one that's going to require I mean, we have to think a little bit about what a could be, but let's put that aside. Let's put this whole thing aside because they haven't taught it yet. Okay, the volume would be a times a times a. The area of one of the cube faces would be a to the second power. Okay, so this one's a freebie for you. The answer is diagonal of one of the cube's faces. A little preview for you of something we're going to learn later. All right.